Assistant Professor, Department of Civil Engineering, Hindustan College of Engineering and Technology, Coimbatore. And today we are going to see about the moment distribution method of an analysis. The objective of this topic is to understand the basic concept of the moment distribution method and also to analyze the indeterminate beams, frames and etc. by using the moment distribution method, and it was introduced by the Hardy-Cross. Introduction. The moment distribution method was first introduced by the Professor Hardy-Cross in 1932. The moment distribution method has remained the most popular method of tackling indeterminate beams and also the rigid frames, and it uses an iterative technique, and this method employs a few basic concepts and the few special terms such as fixed end moments, relative stiffness, carryover and distribution factor. General principles and definitions. The moment distribution method is a method of a successive approximations that may be carried out to any desired degree of an accuracy. This method begins by assuming each joint of the structure is a fixed. So here we can't use the simply supported or a roller support. So we just assume that each and every joint is a fixed joint, and by unlocking and locking an each joint in a succession, the internal moments at the joints are distributed and balanced until the joints have rotated to their final or nearly final positions. Fundamental proportions that we have been used in the moment distribution method are as follows. Next, fixed end moments. All the members of a given frame are initially assumed to be fixed at both ends, and the loads acting on this fixed beam produce the fixed end moments at the ends. And there are the moment exerted by the supports on a beam ends, and these moments keep the rotation at an end of the each member is a 0. And since here we need to assume that all the joints in a frame are assumed to be fixed, why we are not using the hinged structure or a roller supports? Since if we use the hinged or a roller, the rotation, that is the movement at that joint, it will be of a 0 since it has been in a released state. But in an arrested state, how much the movement has been exerted at that joint has been found out only at the fixed end. So that here in a moment distribution method, we are assuming that each and every joint is a fixed end connection. Stiffness is generally taken as the force required to produce the unit displacement, that is, force by displacement, and it is also the moment required to produce the unit rotation at a specified point in a beam or a structure, and it can be extended to denote the torque needed to produce the unit twist, and the stiffness is usually denoted as a K and can be proved to be given by, and K is equal to 4 EI by L, fair and is a fixed. If you are considering this beam of an AB, so we need to find the moment of an AB, so MAB. So here M will be indicate that moment and A indicates that nearer end and B indicates that far end. If B end is a fixed condition, so we can going to use the formula K is equal to 4 EI by L, and since we are going to take MBA, so moment about a BA. So B is the nearer end and A is the far end. Since A is a hinged support, we are using the formula of K is equal to 3 EI by L. And it is easy to realize that K will be large if E, Young's modulus, and I, moment of inertia, are large. And same way, K will be less, that is the smaller value, when length L will be more. That is, L is inversely proportional to K and E and I are directly proportional to K. And look at this figure. So that is the displacement. The force has been here, it will be of a moment. By applying a moment, it can go into displacement, that is the theta value, it will be equal to 1, that is the unit displacement. That is the definition of the relative stiffness. So by applying the force required to produce the unit displacement, that is the theta is equal to 1. Carryover. In a moment distribution method, we must analyze the effects of applying imaginary moments at a specified point, the beam shown in the figure, and look at this figure. And when it receives a moment M at A will develop at a B a moment of an M by 2. Since when you apply a moment at an A, that is when you are applying an M moment at A, there will be some sort of the moment has been developed at a B. That moment will be equal to n m by 2. The value will be equal to n m by 2. This m by 2 value is called as a carryover moment, and the factor 1 by 2 is then the carryover factor. So the 1 by 2 is also called as a carryover factor. If the fair end B were hinged, so if you are taking a moment MAB, so the fair end B will be hinged. So since the fair end B is hinged, the carryover factor it will be of a 0. Distribution factor. A movement which tends to rotate without the translation. A joint to which the several members have been connected will be divided amongst the connected members in proportion to their stiffness. For an example, if a beam BA, DA and CA are connected at an A, and if the rotation theta is given to the joint, so the rotation has been given to this joint by an external moment of an M. So each and every member at BA, DA and CA has been rotated towards the rotation of an angle theta. By applying an external moment M, the rotation at the joint of each member, it will be obviously a theta. And the moments AB and AC and AD, the sum of moments will be in the ratio of a K1, K2 and K3, where K1 is the stiffness of the member AB and K2 is the stiffness of the member AC and K3 is the stiffness of the member AD. And here the summation of K, it will be the total stiffness, that is the summing of a K1, K2 and K3, and where M is the total moment that has been applied. So we can find the moment AB is equal to K1, that is the stiffness of member AB, divided by total stiffness of the object into moment applied. Same way for an MAC and MAD. The factors K by summation of K are called the distribution factors. Moment distribution procedure. The moment distribution method is an iterative procedure, that means of the continuous procedure. To start with, all the joint in a beam or a frame are considered as a fixed. In case of a simply supported, hinged or a roller supports, the fixed end moment will be considered as a 0 and the given load applied on this modified structure. Just we are going to start the problem analysis of the structure by a moment distribution method. We can start it with the beam having a fixed joint, and under this condition all the joint moments can be considered as a known. In case if it is a simply supported moment, the value of the fixed end moment will be 0, and in case of a fixed end conditions, we are knowing the formula to find the fixed end moments, and these are called as the fixed end moments. The various steps involved in the moment distribution procedure are as follows. And the simply supported ends cannot have a moment. If they have a moment, the simply supported ends does not have a moment, and if there is a sometimes if it is having a moment, this moment shall be removed by applying equal and an opposite moment there. So if in these cases, if there is a moment like this, so if we are in a clockwise direction, we are going to apply a moment in the anti-clockwise direction, that means of an equal moment, so that the total moment it will be 0 here. And same way, and in these cases, interior joint cannot have any net moment, and if the sum of the moments summation of M at an interior joint is not 0, it must be 0, and if it is not 0, it is an error. So to offset this error, a balancing moment of minus summation of M, so total moment minus summation of M shall be applied at that joint. If you are going to give a moment of, and this will be the summation of M in the clockwise direction, so we can take it as a positive, and the same way the summation of M moment has been applied in the negative direction, so that the total moment here it will be of a negative moment shall be applied at the joint. And here the third point, the balancing moment will be shared by the members. So here the balancing moment will be shared by the members connected to the joint in the ratio of their stiffness. So according to the ratio of their stiffness, the balancing moment has been shared between the members in case if a joint B and left side there will be a member of A, and then right side there will be a member of C. If a joint B, if we are going to take a joint B, and it has been looking like this. So for a joint B, if you take a joint B here, and the balancing moment, the moment has been shared by the member of an AB and also the member of a BC. So this is what that we have been seen here. Now each of the balancing moment introduced in a members, that means of a step 1, 2 and 3 in the previous slide, and will induce a movement at the opposite end, so that in case of a BAAB that we have been seen here, that induces the movement at an A also of the member, and it is a carryover movement, and the carryover movement so induced will again spoil the balance achieved in the steps. So in a balancing movement the structure has been balanced, by after the carryover it spoils the balance achieved in steps 1, 2 and 3, and it needs to be balanced once again. And this process of balancing and also carryover shall be carried out till the values of the moment involved in the balancing are negligible, and the whole process is systematically carried out in a tabular form, and the sum of moment at an each end of an each member received in the balancing process and carryover process has been taken as the final moment. I hope you understand the basic concepts of moment distribution method. Thank you.